Hello, and thank you for viewing this presentation which was given at the EUCNC 2026 Workshop 5, which asks whether there is anything genuinely new for security in 6G networks. MARE addresses this question, proposing a programmable, modular, and disaggregated security plane for 6G ecosystems, designed to support operational flexibility and stronger security assurance. This presentation will explain the vision of the project, the main building blocks of the architecture, the role of the so-called security functions, and why pre-assessment is important to achieve trustworthy security automation in 6G. The main objective of MARE is to create a reliable 6G services provisioning platform through the definition of a security plane built from open and programmable security functions. The project's two major innovations are, first, the move from relatively static network functions virtualization-style thinking toward richer, composable security functions, and second, the introduction of a smart pre-assessment sandbox where those functions can be analyzed before production deployment. MARE therefore combines reactive protection, proactive prevention and validation before enforcement into one coherent framework. If we had to capture MARE in a set of keywords, they would include terms like softwareized, dynamic, adaptive, modular, open, predictive, proactive, reactive, and pre-assessment. These words reflect the core design principles of the project: modularity, programmability, adaptability, and the ability to test actions before committing them to a live network. Impact analysis is also a key term here, because MARE is not only concerned with detecting threats, but also with understanding the consequences of both attacks and mitigation actions. We now introduce two central ideas in MARE. The first is the softwareization of security through dots and security functions, where smaller building blocks, so-called dots, are composed into higher-level capabilities, i.e., security functions, rather than treated as isolated tools. The second is the use of a pre-assessment environment, based on early modeling and digital twinning, so that security functions can be evaluated as sandbox solutions before they are deployed in the operational network. MARE works with dots, representing assets and tools that span many different cybersecurity areas, such as monitoring and analysis, detection, cyber threat intelligence, assessment and enforcement, and data, and network digital twin models. Those dots are then composed into security functions that provide more complete, reusable, and operationally meaningful security capabilities for the 6G environment. This gives us an idea of what the MARE ecosystem can become and how big is its potential when all the ideas driving it are put together. A fundamental component in the definition of a strategy for security provisioning is the proper identification of the potential attacks and vulnerabilities this strategy must deal with, i.e., the attack surface. MARE structures the 6G attack surface into several thematic areas so that threats, requirements and validation efforts can be treated in a systematic way. These areas include cloud-native disaggregation and O-RAN, AI and analytics, heterogeneous edge resources, network capability exposure and network of networks convergence. Each of these are associated with several envisioned attack families, driving the set of proof of concepts to be considered in MARE for development and validation purposes. This mapping is important because it links architectural risk areas to validation scenarios and to the security functions that MARE is developing. Here we see the main MARE functional modules assembled into one architecture. The abstraction layer collects and structures telemetry and system knowledge. The cybersecurity core provides design, security function composition, and adaptive orchestration, and the pre-assessment stress testing environment supplies the pre-assessment and validation capabilities across simulated, emulated, and real contexts. The interface layer exposes services such as visual mapping, intent-based networking manager, APIS, and SSLAs. This is what allows MARE to support both reactive and proactive security workflows in a single programmable security plane. We would like to emphasize that MARE is not just proposing components, but also addressing a difficult systems engineering problem. The main challenges include connecting the dots, composing security functions, running trustworthy pre-assessment, managing inaccuracy, defining SSLAs, designing the bootstrap process, and deploying the complete solution end-to-end. The novelty in MARE is not a single algorithm or module, but the orchestration of all these aspects into an integrated 6G security framework. Each of the observed questions is deeply analyzed next. When we ask how to connect the dots, the first issue is to define what a dot actually is and how it should be represented, catalogued, and exposed. In MARE, dots are treated as fundamental security building blocks, but they must also be discoverable, described through metadata, and related through compatibility and interface information if they are to be composed at scale. The long-term goal is therefore not a fixed static list, but an evolving ecosystem of reusable building blocks supported by repositories, APIS, and structured descriptors. The next question is how to compose security functions from those dots. MARE approaches this through a security function composer supported by a knowledge base, discovery mechanisms, repositories, and live information about the status of the available components. The purpose is to either generate or select the right security function for a given situation and turn available security assets into actionable and context-aware protection strategies. The basic idea to perform pre-assessment in MARE is that after a security function is composed, it should not move directly into deployment, but should first pass through the pre-assessment stress testing environment, where the testing environment manager and the pre-assessment and validation modules are evaluated against several well-defined policies, expected impact, and contextual constraints. The no action without preliminary testing loop and the what-if loop highlights two important ideas: analyze before acting, and explore alternative actions and outcomes before committing to one in the live system. Inaccuracy is one of the hardest problems in any automated security system, and MARE makes that explicit. Inaccuracy may mainly come from wrong predictions inside the pre-assessment environment or from wrong detections in the real infrastructure, so MARE does not assume that AI outputs or analytics are automatically trustworthy. Instead, the project uses model thresholds expressed through SSLAs, continuous telemetry, and impact analysis in the pre-assessment stress testing environment to reduce the risk of acting on weak or misleading evidence. This is why the SSLA is more than a policy document. In MARE, the SSLA is used to support pre-assessment, configure security functions, and define acceptable thresholds, including thresholds related to model accuracy and operational behavior. Just as importantly, the SSLA is intended to remain open and extensible so that it can evolve with services, infrastructures, and threat conditions. The bootstrap process is one of the points where the architecture becomes operational. On the southbound side, the abstraction layer ingests telemetry, topology, and system data, enriches them, and feeds the cybersecurity core. On the northbound side, operator intent flows through the interface layer, where the intent-based networking, SSLA management, repositories, composition, and orchestration translate high-level goals into executable security behavior. The important point is that MARE links infrastructure observability, intent handling, policy activation, security function preparation, and steady-state monitoring into a coherent startup and runtime process. This slide visualizes the bootstrap process. The two diagrams show how information and control flow through the abstraction layer and the interface layer, clarifying how telemetry, topology, threat models, SSLAs, repositories, composition, and orchestration are coordinated across the architecture. MARE is therefore designed as a conceptual architecture and as an integrated sequence of interoperable workflows. Deployment is another critical part of the story. The architecture shown highlights that MARE is also about deploying and coordinating various functions through the cybersecurity core, the pre-assessment stress testing environment, the abstraction layer, and the interface layer, with orchestration playing an important role. These components are implemented as cloud-native microservices connected through standardized APIs and common data models, which is what makes scalable integration and iterative releases possible. To summarize, MARE first studies and categorizes the evolving 6G threat landscape. It then develops enriched security functions as modular software blocks, and complements them with a smart pre-assessment environment spanning simulation, emulation, and real infrastructure so that security services can be analyzed and tested before deployment. More broadly, the project contributes methods, architecture, and validation practices for addressing the diverse challenges of 6G security provisioning. Thank you very much for your attention. MARE is building a programmable, modular, and disaggregated security plane for 6G ecosystems, and this presentation has focused on how composition, pre-assessment, orchestration, and deployment fit together in that vision. Please follow the project through the listed channels, and thank you again for your interest in MARE.